Welcome back. I'm going to be studying this afternoon, working again on quantum mechanics. So what I've been working on is getting through my big sheet of things to do here right now. I've got a cat sitting right here. I'm going to push you up a little bit. Okay. There you go. There you go. All right. I've got this little to-do list here. This is after I went through all of the lectures and the problem sets. I kind of figured out what don't I understand. Made some lists here of concepts, facts, and skills, and I also made some problems that I wanted to do again, and some of the ones that circled are ones that for whatever reason I didn't do the first time. So you can see a lot of these things are crossed off, which means I've been making progress on my to-do list. I have done the ones that I've crossed off a second time. It doesn't mean I got them all right. It just means I've done them a second time. And I wrote in pen here for ones that I might do a third pass on. I don't know, third pass is then kind of pushing it a little bit, but some of these do represent concepts that I wanted to work on. So for this question here, there was a different way of solving it, which I wanted to try out. And I think these two here involved solving for the eigenfunctions of energy eigenfunctions of these wells and scattering states and stuff, and so it's all matching boundary conditions and this kind of thing. And I wanted to get a little bit better at that because I was missing some of the simplifying assumptions that were making those problems tractable. I also have some concepts that I still want to review. So I'm going to work this afternoon, see how long I can put in today, and then tomorrow I'm going to work on it. At this pace, I'm probably going to want to work a little bit on the weekend. Just because I haven't finished all the things I wanted to cover, and I do have a bit of time this weekend to work on it. Of course, at the end of April, the project's over. It doesn't mean that, I'm done learning quantum mechanics. It just means that, I'd set aside a month to work on this where I'd cleared off some of my other work. Once May rolls around, I'm going to be busy again, going to be working on other things. So even if I keep working on this, I'm probably not going to be able to keep it up at this kind of pace. So, I think if I finish this, unless the exam goes really terribly, I might move on to watching some of the lectures of 805. That was kind of the trigger point for watching this, is that I watched some of the lectures of 804 about a year ago. And I was like, oh, wow, I don't understand what's going on. I need to actually work through these problems to understand it. And so that was sort of part of the motivation for doing this in the first place. I don't know whether I'm going to do an ultra learning project for those later classes, or even anything really. Like, there's always so many things I want to learn compared to how much time I have. So choosing what to do ultra learning projects for is itself a little bit of an art. So I'm doing this right now, and that's all I can say. So where I left off this morning is I was working on this question 8.5a, which, I'm making a big issue out of this here, but I don't know what I'm doing wrong. I have done this question before, so I can even say that. This is not like it's not even like this is the first time I've ever seen this problem. And yet, for some reason, how to do it is escaping me. So let me just sort of speak out loud, because this can be helpful for me, even if I don't even know whether anyone's watching right now. So basically, what we have to show is that in a spherical harmonic, meaning that there is a definite value of angular momentum in the z direction, it could be 0, but it's definite, as well as obviously a definite total angular momentum, which is always possible. That in this particular case, we have this wave function. Oh, hello, cat. Are you gonna come paw my notebook while I'm studying? We want to show that the expectation value for the x and y direction for the angular momentum is 0. So this, I don't think, I think that there's, so that the idea here is, if we were to express this in terms of, so obviously the expectation value of one of these operators is equal to this inner product right here, YLM, and this times this. And we have these plus and minus, these raising and lowering angular momentum operators. And my thinking is that we're going to add 0 somehow. And by adding 0, either by, lowering this down to -1, or by adding a plus and minus ILY, something like this, that we're going to end up with things canceling. So one thing that is useful to note is that if we can get a clean inner product of these two without the operators, and these numbers are different, so if we have different m's, then these are orthogonal, so these are going to be 0. Similarly, if we have, you know what, I'm thinking about how I can do this. So this method I was trying out here was, well, what if we lower it by 1 and then add the raising operator here? And then I expanded it out, but this doesn't seem to be helping, because then I'm going to get an LX squared, and then I don't know how things are going to cancel here. So I tried commuting it through, but I still have the LX squared. Now I have this LZ. I don't know. This doesn't seem to be any better. So what other things can I try here to get this to? Because it does equal 0, so we're going to show, we want to show that it equals 0. What was it that because I tried the other way of, no, this was with the raising. I had tried it over here where you kind of add 0, and then I have L minus plus ILY on this. But this didn't seem to get me like any further, really. I mean, this is not any, like, this just reduces the problem to, the other one we have to solve, where we just swap y for that. So, let's see, what other options do I have for manipulating this into getting them to cancel? I'll just put this over here. Okay. Another option we can have is we can try to move something from, I think it has to be on this side. Yeah, it has to definitely be on this side of it has to be the outside operator. I can bump it over to here by taking the adjoint. I mean, this has no obvious adjoint here. What other things can I do? I think the other thing I had tried was to do something like maybe getting the raising operator here. So we have, what is this? And then if this is the raising operator, we have y of L m minus 1.
Let's go back to problem 3 and look at some of these commutator relations to see if there's anything I can do here. Okay, let's try this, because we did get YLM minus 1. And then when we commute this through, I think Lx is just Lx, and then it's going to commute to minus this is going to be, I think, did I work that out? Is it minus h bar Lz? Because our commutator of Lx and y should be h bar z. Hold on a sec. L x and y is IH bar LZ, so this is going to be minus IH bar LZ. So I think this is right. And we have YLM. And then what was the idea here? We want minus here. Minus plus 1. Yeah, this isn't obviously helping either. Oh. Yeah, I give up. I've spent 3 pages on this. I can't figure it out. 5. We want 5. Where's 5? Oh, geez. Okay. So L plus is equal to Lx plus I Ly. L minus is equal to L minus I Ly. Lx is equal to L plus L minus divided by 2 equal to L plus minus L minus divided by 2I. Is equal to L plus L minus YLM. YLM plus 1. And these are each equal to 0. Wow. Well, there you go. I don't know why. I didn't see that. All right. Cross this off. Oh, 8.6 I have not done. So this is a new question. Lifting the degeneracy of the quantum rigid rotor. Oh, why didn't I do this one? Consider a spherically symmetric rigid rotor. The moment of inertia Ix equals Iy equals Iz equals I. Classically, the energy is given by. So we have some kind of sphere like this. And so spherically symmetric, E is equal to squared over 2I. What are the energy eigenstates and eigenvalues for this quantum rigid rotor? So I think we're going to get E. So E should change this to let's get the same notation. What are the energy eigenstates? Well, how are we going to get the n dependence? Let me look back at my notes on this problem. So this is very similar to when we were trying to do, I was in a central potential though. I don't think there's no potential here, so I don't think that there's any n, so we can just go right? Like it's just LM. Oh my god. Cat, move out of the way. Out of the way. Hey, your tail over there. All right. Because when we had the Coulomb potential and the central potential, there was a potential. So there was, the same kind of bound states that we had in the first situation. Here, there is not. So my guess is that this is just L and M. Would this not be the spherical harmonic? And there's no M dependence. So what's the degeneracy? There's got to be an n dependence because n is the total. So is it like n equals L? Is it 3n n plus 1? Because you got each of the three directions. This is a real guess.
All right, let's look 6. Okay, I guess just cancel this off, but yeah, basically. Given it doesn't depend on M for number L, there is from minus L to plus L. Therefore, degeneracy of EL uh, 2L plus 1. Okay, good to know. C. Sketch the, what are the new energy eigenstates and eigenvalues? So, what happens when we shift in one direction? Well, we're going to have ELM is equal to it's going to be h bar squared L plus 1 over 2I No, I'm double counting as we've greatly increased the energy. So which one is going to get deleted here? Is it this L? Yeah, I think it's this guy here. Right? Sketch
spectrum of energy eigenvalues is a function of epsilon. For what sign of epsilon do the energy eigenvalues get closer together? Intuitively, why? So let's just go here. And so this is going to be our L equals 0 state. And then our L equals 1. And there's going to be two options, m equals 1 or m equals 0. So if m equals 1, it's going to lower it here. And this one's going to go a bit higher. And it could be the opposite, no? And let's say it's up here. Oh, hold on a sec. What's going to happen exactly? So in m equals 0, it's just going to be this guy. Which is going to be the same as, hold on a sec. M equals 0 is just going to go like this. And then m equals 1. This is going to go down a bit. And then we have m equals 0 again. But this time it's a negative epsilon, so it's going to be decreasing, but it's a slightly larger factor. So I'm going to say m equals 1. This gap. So right-hand side gap is larger than, oh, left-hand side. Left-hand side is larger, right-hand side. Or closer for positive epsilon. Intuitively, that would be because if we smush it, we're kind of squishing it out to all sides, whereas if we lengthen it, we're shrinking both sides. And then this guy here, let's do 3 here. So we're going to have again m equals 0. equals 0. And then we're going to have, this is going to be L. L equals 2. Then we're going to have 1. And so for 1, these are both going to be 1. We're going to have half of the way they did for before. So it's going to be a little lower, but half as much. And then these are going to be same but higher. M equals 1. So these are actually the same. And then we have the 2 staked. Okay, cat. Scooch this way. That's my guess. What's the degeneracy of the nth energy eigenvalue? Actually, it's not this. It's the absolute value of m. So E, no, not fully lifted because ELM equals EL minus M. To lift fully, what will we have to do? To lift fully, how would we break all the degeneracy? So we have to make it so that if it's spinning this way, like spinning this way, versus spinning this way, there would be a difference. Oh, that's a hard question. My suspicion is to break the rotational symmetry, so also just I x2 I x1 plus, let's go beta. That would be my guess. All right. So this was not right. I'm going to do C here. So we have to do E is equal to Lx squared plus Ly squared 2I is equal to Lx squared minus Lz squared. So we're going to have now h bar squared L plus 1 h bar squared m squared over 2I epsilon plus epsilon. Is this factorable into what I did? Because what did I have? I had h bar squared m L plus 1 or 2I. Oof. Are these equivalent? Maybe I'll just put in some hypothetical numbers just to see if we have any chance before I run any calculations. So let's say L equals 3, M equals 2, I equals 4, H bar equals 7. So then this would be 49 times 3 times 4. Over 8. And then this one here would be 49. 4 times 1 over 8 plus 49. 2 times. Even close to the right thing. I mean, this is not a proof that they're the same. I just want to see if I want to put in a few numbers, if I'm going to waste my time trying to reorganize it, or if I just got it wrong. 49 times 12 divided by 8. Okay, so this is 73.5 minus something, and then this is 49 times 4 divided by 8, 4.5. Minus 2.22. This is 49. 2 times 4 divided by 8.8 to 44.54. So no, these do not match. So I got it wrong. All right. So I think I was just guessing, and I think that's my mistake, is that I should have broken it apart here. All right. And then the sketch is going to be a little different too. Yeah. Okay, so I did get this part right at the end, but I got this wrong. Okay. I mean, I hadn't done that question before, and it's been a long time since I learned this moment of inertia, so I don't feel too bad about that. 9.2a, 9. Hmm. 9.2a. Consider an electron trapped in a Coulomb potential in the state corresponding to the maximum orbital angular momentum, L equals n minus 1. Oh. This cat is just sitting right here. All right. I just wanted to do A for this question. Show that the expectation and R are not n plus 1. Oh, this is this god-awful thing with the Laguerre polynomials, right? So R is just going to be phi of n minus 1. Guess it doesn't matter, but I'll just put 0. Actually, I can just put m because I know it doesn't have any m dependence. And then this is going to be R. And I need to figure out what the form of this is. Do I have it written down in a place where I can look without looking at the answer? Because I think this one used the closed form. I don't think I have it anymore. I have to go back to where I did this. Problems at 8 here, we're from problems at 9. So let's just get this part and not do anything else. So we have y, phi NLM r theta phi is equal to 2 over n r naught n minus l minus 1 factorial 2n n plus l factorial 1/2. And then we have e minus r over n rho Laguerre polynomials. So we know this is going to be just 1 for this, so I can ignore it for right now. 2r y l m. Okay. So basically what we're doing right now is taking complex conjugate of this and multiplying it by r times this one. So that's going to give us what? I don't see any i's in here, so the complex conjugate's just going to be the same. So immediately, so we're having L equals n minus 1. So let's just take this guy right now. We'll just take it squared. So it's going to be 2 over n naught cubed. And L plus 1 is going to be n minus 1 minus 1. So that's going to be, hold on a second. And then we're going to have right. Except on each side, this is going to be an integral. Multiply these two, so we're going to actually add r squared. So this is going to be r cubed sine squared theta, right? So this whole thing is going to cancel off of this. And this n minus n. This whole thing is going to become 0 factorial, which is 1. 2n. So what are we going to have here now? We can bring a bunch of this out. Right? I can bring a bunch of it out. So everything that doesn't involve one of the variables of integration right here, we can just pull out. So, oops, what's the point of pulling it out if I put the integrand first? That's going to be 2 over n rho naught cubed 1 over And then we have, do we have anything else that pulls out? No. D omega, and then we're going to have sine squared theta should cancel when we integrate over theta, because none of the other terms are in theta. So when we integrate over theta, it should cancel, right? Because two pi times theta is 1/2, right? Or 1/2. And because there's two of them, it should just be 1. So I think we can just make that equal to 1. And I think this YLM we can also make equal to 1. That just gives us these guys. Mm-hmm. This is just 2n factorial, right? Let me combine them. So we're going to have 2 to the power of 2n r 2n plus 3 all over n rho naught I think we can just pull this guy out too and just put a squared here. Not squared, actually. Oops. Let's leave it in. I don't want to write it elsewhere. And rho naught. And then this is going to be what? Integration by parts. 2 over n rho naught cubed. 1 over 2n factorial. So we're going to have this 2 to the 2n r to the it's actually 0. What was it? 0 to infinity, right? And this integral is what? What's the integral of? Actually, I don't think I want to do it that way. I'll do it the other way, right? No, there's only a single r there, so integral of that will just be the same thing, but a polynomial is going to get dwarfed by an exponential. That's going to cancel, right? This 2 to the n, 2n r, 2n plus 3 over n rho naught times minus n rho naught over 2 e to the minus 2r n rho naught. This is evaluated at infinity is going to be 0. And then we're going to have plus the integral of what is it? It's uv minus e prime u. Is that it? Or do we do it the other way around? And I cannot remember my integration by parts for the life of me. I should make a flashcard for that. Let's do one. Why not? No, it's u. U prime. All right. And so this is going to be our, what did we pull out in front? Pull the u in front, so it's going to be u prime. So this is going to be 2 to the 2n 2n plus 1. We're doing, yeah, 2n plus 1. Does this work? What am I doing? Oh, what am I doing wrong here? How do I evaluate this integral properly? I'm just going to draw a line through this. Hmm. Do we have some kind of recursion relation here? Like, what's happening? Because we take the exponential on the outside. We integrate this whole thing between 0 and negative infinity. 0 and infinity, it's going to be equal to 0. Well, at infinity, it's going to be 0, and then this is at 0. It's just going to be equal to 1. It's just going to be 1. And then, which was the outside guy? So we want to lower the order of this each time. So if this equals u and this equals v, we have u, v minus u prime, v. You get this polynomial times the exponential minus number one lower. So is the recursion relation going to be so each time we take it down by 1, what's going to happen? So this is 0. It's going to be just this. So we're going to get 2n over n r naught
Oh, this is messy. What's the answer? So the answer was it's equal to this, which is not super obvious, but 2 over NRO negative 4 is 2n plus 1 factorial. This cancels with this, and this cancels with this. We have it equal to n r naught over 2 times 2n, and cancel r over 4. Oh no, what did I do wrong? 3 minus 4. Oh, it's 2 plus 1. So this is 2n factorial. We get 2n plus 1. And then this is minus 4. This is minus 1. N r naught. So we get this. Wow. Okay. I think that the problem was just solving that recursion relation. Really messy. Okay. Moving on. Oh my god. Cat. You need to go sit over there. All right. Now I want to do 9.4 E and F. Oh, this is the solutions. Okay. No wonder I was like. Hey, you gonna get down? Yeah. Hey. Okay. There you go. So we're
experimentally, if we excite a physical hydrogen atom from, how much angular momentum would it emit in the process? So we're going to go from 1, 0, 0. We're going to go from, hold on a sec, 2, 1, 1 to h bar squared. Two, right? Because it's 1 plus 1 times 1, right? Which angular momentum would it emit in this process? It's 2 h bar squared, but that's not even right units for energy. What's the right way to get this into the state we want? Do we have the energy eigenvalues of the Coulomb potential on this? I don't think we do. So I think this is one of the ones that I wanted to write down. I think it's like n squared, right? Which angular momentum? Well, what is this in units? This is kilograms meters squared per second. So we would need it to be divided by a length. Right, because kilograms meters per second is what we want. It's 2 h bar squared something. Let's look at E. Oh, it is 2 h bar squared. What? Feels like the wrong units. Huh. Joules seconds squared. Wait. We've had, this is h bar. Kilograms squared meters fourth second minus 2. Just seems like the wrong units. Oh, yeah. All right, well, 2h bar squared. What will the wavelength be? So we have 2h bar squared is equal to this is our angular momentum. So lambda is going to be equal to 4 pi h bar. So this isn't even the right units. How is this? This is the wrong units. What am I doing wrong here? So lambda it seems wrong by dimensional analysis. Like this is an energy times time squared. This isn't an energy. So like if we have 2h bar is equal to it's 2 pi h bar. Doesn't really matter, I suppose. I mean, what am I doing wrong here? Why is this giving me... What's the classical... rotational kinetic energy. Now I have no idea what's going on with these questions. Because you put this in here, you have EV times seconds, and this is meters. So you have EV seconds squared is equal to EV second times meters per second. So let me just see what, like, if they're getting something. So we have EV times seconds is equal to squared. So I'm going to put 2 here. Which, I mean, makes sense because this is supposed to be an energy. This is an energy. Yeah, I don't know how to go from angular momentum of the photon to energy. All right, I'm gonna just leave this because I have no idea. No idea how they're getting the units to convert here. All right, let's put a slice through this right now. And I'm on to number 10. And I'm wondering whether I want to take a little break from doing these because I wanted to do, did I do crystal momentum? I think I did. Where's my crystal momentum? Okay, I did deep dive on that. This, ratio of parts, Taylor, substitution variables, delta function normalizability, G naught, crystal momentum. Yeah, I think I wrote it down, but I don't think I actually went back through the lectures. No, I did. Yeah, okay, so that is done. I just didn't cross it off here. So maybe I'm going to take this as an opportunity to go through a few of these guys here. I think I can cross off hyperbolic sines and cosines. I think I want to maybe get a few of these guys. So what are the... I was going to make some flashcards. Get the Coulomb. Where's our Coulomb potential here? Actually, you know what? I think I'm going to leave that. What was it? So let's do a couple of these. I did do crystal momentum, so I can go on to these questions if I want. But I think I'm going to just spend the rest of the day doing a few Feynman techniques to get caught up, and then I'll work on this tomorrow. And it's looking pretty good. I mean, I'm getting through it all. There are a few more questions I singled out to redo. But I think I'm not going to do much more than those, just because I think I want to move on to looking at some new questions, new exams. If I just keep repeating these questions, I'm not going to make much progress. So let's start with Vibenius Theorem. I don't even remember what that was for. Let's check it out. Vibenius Theorem gives conditions which is possible to compute a double integral by using an iterated integral. What the heck was this related to? I thought I would remember it when I saw it. It was something we did more recently. Was it related to, you know what, I'm just going to do a search quickly for Vibenius in the problem set solutions, just so I can remind myself of why I'm even looking at this. I think it would have been in the first 5. Oh. Okay. Thanks to the independence of our 3 integration variables, x, q, and k. This was expectation value. All right. So this was problem set 2.2a. 2.2a. Okay, that's this one here. So let's just, I don't think I need to do a full find for this Vibenius theorem. I just want to look at it. Under which it is possible to compute a double integral by using an iterated integral. One may switch the order if the double integral yields a finite answer when the integrand is replaced by its absolute value. So I think it's just seeing we can switch them around. Couple questions in the chat come up. Do I study chemistry for it, quantum mechanical models? I'm not sure what you're asking, neat study sessions. If you're asking how to study a course in a short period of time, I've written about it on my blog. I don't think that there's much more I can say. You've asked me these questions for a couple days now. I just don't think I have any different answer to give you, I'm afraid. Matan is asking, did you solve one? No, I didn't. I tried, but I failed. How much trigonometry do you need for single variable calculus? You should know identities involving sines and cosines. Not a ton. Like, I mean, you're not doing a lot of geometry in calculus, but you do need to know that, like, sine squared plus cosine squared is equal to 1, or tan is equal to sine over cosine. So there is a trigonometry point, but that's not so much geometry anymore. That's more just like understanding some basic identities. So I would recommend doing it. And if you don't know any of those things, I would just recommend looking it up. So I'm going to ignore Vibenius theorem here. I'm just going to cross this off. So we want to do setting up and solving differential equations. What other ones did I want to do? This is just another form of the Taylor series, which I didn't know. Integrating delta x. I think we did some problems on that. Operators on tilde k. Maybe we'll talk about setting up and solving differential equations. Uh, problem so I should open just the solution so I can see how they're done. Okay. Why is this q to the fourth? Oh, q squared, right? Okay. Okay, so let's walk through that step by step. So what's happening here? What is the thing that we're able to do here that allows this? D dt. All right, that's probably as far as I'm going to get with that. What are some other things I wanted to work on? Solving for the energy values in walls. Okay. Yeah, let's go. Do this first. This is number 3. What's the right way to do this one? How does it work? Well, let's go through our notes. I know it's times that function, but I've struggled a little bit with where do we do delta functions? Switch these guys around. opposite. Why do I have it backwards? Mm-hmm. I must have done something wrong here. Where did it backwards? Minus. Inversely value. Okay. No, this is not B not X. No, I want So how did they get the, which question was this? I think it was 7.5a. This was so why is it C, not something else? I guess it doesn't matter. You could take either side. Okay, I think that's probably good. This is our boundary condition. Okay, I think that's good for this. Excuse me, I'm just gonna use the washroom. All right. Let's see. I had so many questions. Okay. So I'm feeling like I've gotten mostly what I wanted to do here with Feynman techniques. So I think I should just move forward on to these final set of questions. There's 3 more that I might want to do third pass for, not to mention doing a little bit of exam prep. Yeah, it's going on pretty well. All right, so let's shift over to question 10.4. And I'm trying to do all of those. 10.4. Ooh, identical particles. All right. Mm-hmm. Okay. let's verify that x1 and x2 is equal to 0 in all cases. All right, so for our distinguishable case, we have psi d times x1 of psi d well, we can consider them separately because the other ones don't have any influence. So so this is just going to be negative infinity, positive infinity of x e to the, I'm going to just put constant here, x squared over p squared, which is equal to 0. And then our, this is x, yeah, this is x2. Again, is going to be the same thing. But now we have an x term here. So maybe we should just write this whole one out. So so we can just take the 2 over p root pi, and we should have x squared over p e to the it's going to be x cubed over p squared. Also odd, also equal to 0. Now let's try our symmetrical case. All right, so we have they're all real, so it doesn't, I don't have to worry about complex conjugation. So I'm going to have one half psi naught get this 1/2 over here. And then what are we going to have? We're going to have x1 I think if it's times these guys, it's twice squared plus 2x1 we're going to have x1 times sine 0 x2 squared sine 1. I'm going to read x1. Right. Oh, what am I doing? This is x2, x1. So in these cases, we can just use our result from above. So these guys are going to cancel right off the bat. Now we just want to look at this mess right here. That's this one. So I'll cancel this and this, and so we can also ignore these two guys. And so we're going to have these two orthogonal, hence 0. And it's the same for the other case. And then the anti-symmetric case, it's going to be the same thing, but with minus 2x1, x1. One. So again, by orthogonality, odd functions. Okay. A. Let's look at B. Create the mean squared distance in each of these states and verify that. Oh, okay. So that's like so I have x1 minus x2 squared is going to be equal to from And so if this is the expectation, we're going to go Can I use that orthogonality argument here? I don't know whether I can. Because we got this x, so I'm being a little careless here. What is this equal to? Well, we're going to have x squared over rho e to the minus x squared over 2 p and we have that times that. Ooh. Over p root alpha. So it's going to be root 2 over p root alpha, root pi, sorry. And we know that this x squared times this guy is what? That's equal to p root pi. P root pi here. How do I get this to equal 0? Let's try A again here. So our symmetric case, so with our simplification here, So I have to have this and this multiplying and this and this. So we're going to have this root of 1 over rho root pi plus 1 squared over rho e to the x squared over p rho. And then this is also multiplied by same 1 over rho. Oh, but now we only have one of them. We're not integrating over x2, so I don't think that matters. Because this is all just some big constant. So why is it that we get 0 here? Naively speaking, I'm not expecting this to cancel. What am I missing for this to cancel properly? What other tricks could I use to say this would cancel? I mean, do I have to integrate over both? Is it dx1, dx2? Yeah, maybe I have to do that. Because if it's like that, then it'll cancel for sure. That must be the argument. All right, let's look at, so what is it? What question is this? 10.4a, just to confirm that my 10.4a. Yeah, you have to do both. Okay, so that was my mistake, is I forgot you're supposed to integrate both, but then once I've done that, it works. Okay. I'll do the distinguishable case first, because that's going to be the easier order to do. So the x1 term, so this guy going to be equal to 0 because each just the expectation. And then this one here is going to be x1, oh, let's go x1 squared. So this one is also equal to 0 because it is odd. So what this one is equal to is equal to rho root pi ooh. Am I missing something here? Because I'm supposed to be getting rho squared, but I'm still getting 1. This is x1 squared e to the minus x1 squared over rho squared 1 over rho root pi. And if I remember correctly, what this Gaussian evaluates to, it should be rho root pi times that. It's supposed to be 2p squared. Gonna lose the square root e to the minus x squared over 2p squared times e to the minus x squared over 2p squared. E times 4p squared. 4p squared. 4p squared. And because this is 4p squared, that's like 2 rho. Okay, we got the 2 now. Does the rho squared come down? Like, is it? Like e to the minus x squared over 2 rho squared. No, it should be 2 to the e to the x squared over rho squared. What am I talking about? Because these are divided by 2. Look at my Gaussians again. Ooh, so I did get this wrong. This is a cubed. Divided by 2? Did I get that right? So we've got the pi right. Should it be 2 a cubed? Double check. Two. 1/2. So 1/2. N plus 1, so this is 1 plus 1. It's 2 to do 4. All right, this is the yeah. I maybe got this wrong. Let's look at what the answer is for this first part, because I'm getting just p squared. What is p squared over 2? What? Oh. Oh. No, this isn't 0. But we've got an odd function. How did x to the 4th? I forgot this here. This is squared. So this is not odd. Okay. All right. I think given my difficulties and my mistakes in calculating, I think it's a good time to call it a day for right now. This looks like it still holds, so I can don't have to throw that out. I think it was just yeah, just a few mistakes. And yeah. All right, so working through the last problem sets here. What am I going to do after that? I think I'm about good for doing more review and learning once I can get through these problems. So tomorrow, we'll see. We'll see how long it takes to finish these guys. There's not too many left. Let me just jump and look at some of the actual problems here. So we got 10.4, 10.6. Did I not do for some reason? Group velocity. Okay. 10.5a. And then 10.7. Oh yeah, this was a long question. Okay, so it's probably going to take me at least all morning to do the rest of these guys. Maybe all day. I don't know. It just depends on how long it takes. I remember that 10.7 was a real lengthy one. So I'll keep working on this tomorrow. I did have a couple more that I thought I might retry, but I think I might rather shift to looking at actual exams. It's normally I don't like to wait this late to do exam work, so I've mostly been focusing on these problems, and that might be a mistake if the exams are substantially different than this. You know, I don't really know how that's going to play out. So what I'm going to do is, I think after this, I might look at doing some exams even on Saturday. We'll see. I don't really feel like I need to do much more in terms of Feynman's unless something comes up. Not to say that I understand everything perfectly, but I think at this point, yeah, I think most of my problems are on the technical nature right now. So I'll just keep working on it. I'm going to finish 10 tomorrow. Yeah, we'll see. I might see whether I want to work a little bit on the weekend to do a few exams at a time. Monday, I'm definitely doing exams. And then Tuesday, I'd like to do the exam that I have some solutions for. And we'll just see how it goes. Yeah, reaching the end of this. Some things that I would have liked to have done that I have not done is I would have liked to have spent a little bit more time on things of a less technical nature. So I think that might just have to be something that happens outside of the project. There's a kind of process to learning these things where you kind of have to first learn the structure, and then you're kind of building intuition on top of that. And so I'd like to kind of translate this into a kind of non-mathematical intuition about things. I've been thinking about it a little bit, but I've been kind of preoccupied with doing a lot of the equations and building the technical competency first. So that has kind of taken a bit of a back seat.
I do think that I might work on that a little bit after the project's done, maybe put together something where I'm kind of explaining some of these ideas in non-technical language. But yeah, I'll go through it later. So I'm going to be working again tomorrow. I might try to put in a good day tomorrow just so that I can see if I can finish this and maybe start working on the exam. And then I'll just make a decision at the end of the day whether I want to work a little bit on the weekend as well. So it's almost near the end of the project. Definitely a challenging class, definitely a lot of stuff to learn, but it's been good too. I feel like I've also learned a lot. You learn more when things are challenging, I think, than when they are easy. And this has definitely been a case of, a decent challenge level there. So I've gotten brushed up on a lot of the math that I'd kind of let slip over the last 8 years. So I'm going to take leave right now, and I will see you guys tomorrow.